So this is week 7. Oh, not Thursday, it's on a Tuesday. And today's agenda, we are going to look into more detail on shearing stress for non-thin wall structure. Before I go on, I posted the marking scheme on Avenue to Learn. So this is Avenue to Learn to the course. If you go to the table of content, you look at term test marking scheme, you click over here, and here is the marking scheme. And can you all look at your, do you all have any problem looking at your graded term test? Anyone have problem? Are you okay? You all know where to find it? So if not, it's under assessment. You go to assignment and you go to term test. So when you click here, you can look at the remark of your term test and you can compare to the marking scheme. Okay, so if you have any problems with the grading, you can contact your TA first. Okay, so you can contact Joshua Odisa regarding the grading. Okay, if it's not resolved, then you can send me an email. Okay, any questions regarding the reviewing of the term test? Anyone, any questions? Okay, I don't hear anything. So today we are going to go into shearing stress for non-thin wall structures. Okay, so the formula for shearing stress, if I'm going to write the overall general formula for shearing stresses, okay, so shear stress is equal to T R, or I'll call this Tx R over J, okay, and then plus or minus Vy over Izz Qz over T plus or minus Vz over Iyy Qy over T. Okay. So what this equation means, shearing stress can be induced by the first term over here, by torque, or shearing stress can be induced by shear force in the y direction and the shear force in the z direction. Okay, so I will not teach torque. Torque assume to be you have learned in 2P04, which is quite straightforward, which is torque times by radius divided by polar moment of area. More I'm going to focus on is the stress, the shear force inducing shear stress. Okay, so let's look at the theory. Okay, as I said, the formula is pretty straight. Let me write up there. There are two formulas that you have to apply in shear stress induced by shear force. One is Q is equal to VQ over I, and the other one is shear stress is equal to VQ over IT. Okay, so let's go into the theory of shear stress is equal to VQ over IT. Okay, let's go into the theory. So I've posted some images online or figures online which you all need to access. Okay, so it's on week 7. If you all could retrieve the figures, it will be fantastic. Right, so let's look at this figure over here. And what we realize that if we were to draw the transformation, we know that this is our y, and this is our z. So what we are looking down here is the cross-sectional view. Okay, we are looking at the cross-sectional view. Okay, so the thing that we're going to do now is we're going to derive. Okay, we're going to derive the shear stress equation. That specify the shear xy, right, is equal to 3/2 by over a, and then multiply by 1 minus by y squared over c squared. Okay. And you can see on the figure what do we mean by c. Okay, so this c is going to h over 2. Okay, this is c. And what you see over here, okay, what you see on this zz line, okay, these are the centroid. Okay, so for now we are just going to focus on the shear stress induced by Vy. That's why the centroid is that axis is on the z-axis. Okay, so we know from the equation from shear xy, the general form of the equation is equal to Vy over Izz Qz divided by T. Okay. So before I go on, the reason why we are going to derive that, I need to do a setting change. I do apologize. Okay, the reason why we are going to derive, okay, we're going to derive this relationship that I'm going to put in a box, is we need to specify some rules that we need to use when analyzing the shear stress. Okay, or analyzing the shear stress or the shear force inducing the shear stress. Okay, so first of all, I'm going to construct our Vy. Okay, so this is the direction of our Vy. Okay, that's the way. And then we know that the general formula is shear xy is equal to Vy Qz Izz over T. Okay, so what do we mean by Vy or shear xy, which is the shear stress on the x on the plane intersecting the x-axis and the shear stress is in the y direction. Okay, that's why we have shear xy. And then Vy is the shear force in the y direction. So in terms of units, we have this as Pascal or pounds per square inch. Over here, we have Newton, and then this is pound. Okay, and then we have our Izz is the first moment of area, second moment of area. Okay, second moment of area about the z-axis. And then Qz straight on Qz, because it is one thing that it can be confusing. Okay, it is equal, Qz is the first moment of area about the z-axis. Okay. So the formula for QZ, since we are in the first, okay, is equal to A y bar. Okay, where A, so I will put it in a box because it's a formula. Where A is the defined area. Okay, so defined area can be meters squared or inches squared. And the y bar is the distance between the centroid I'll call it global centroid, okay, to the centroid of the defined area. Now talk a bit about the defined area. Okay, so if you look at the structure over here, if you look at the figure over here, the shaded region, as you can see, which I will draw a red box around the shaded region. Okay, as you can see, I'm drawing the round box around the shaded region. This is known as the defined area. And the defined area is a variable. Okay, it is dependent on the y distance over here. Okay, dependent on the y distance over there. And the C prime, or the C prime that you see over there, okay, the C prime, okay, where you see C prime, you have a distance known as y bar. Okay, and this y bar is the distance between the global centroid to the center of the defined area. Okay, so this is the centroid. I'm going to draw in green. This is the centroid of the defined area. Right, again, it's a variable, right, and is the distance between the defined area and this centroid where I draw in Z. This is the global for the entire structure. Okay, so as you can see from here, okay, that is how we determine first moment of area. Okay, so what else? T, we have over here, we have T. T is the thickness of the defined area. Okay, so what you see over here, the thickness, which is a T, is equal to what? It's equal to B. Okay, now the relationship you see over here, where shear stress is 3/2 Vy over A, y1 minus y squared over c squared. This is only suitable for constant thickness. Okay, so as you can see in the diagram, B is a constant. Okay, it did not change at all. Some structures will change. Later on, we'll do some problems where the thickness actually change. Okay, but for this case, it's a constant. Okay, right. So from here, we're going to specify rule number 1. Okay, I'm going to write rule number 1. And these rules are very, very important. We cannot break any of them during the analysis. Okay, So let's look at rule number 1.